All right, welcome to another lecture in this course. So we're going to look at the exponential, at least sort of a quick definition of the complex exponential. That's subsection 1 to 1, and going to look at polar coordinates in complex numbers using the exponential. So that's subsection 1 to 2. All right, so let's define the complex exponential, so e to the z for a complex number z, and we're going to use the real exponential, so exponential for the real numbers, and the real versions of sines and cosines, right? And so the way that we define the exponential, any one of these expressions, so e to the z, if z is x plus iy, we're going to define it using this expression over here, right? And you'll notice that this e to the iy, right? That's what you get was if x was, let's say, 0, right? You'd get cosine y plus I sine y, right? So that's another way, sort of shorter way to write it if you define e to the iy, which we'll sort of talk a little bit more, talk about a little bit more in a little bit. All right. So let's some immediate properties. Let's look at some of these just from the definition. Well, we have e to the conjugate of z, so e to the x minus I y. Well, you just write it down. You stick it into the definition, and you notice that cosine is even, right? So cosine of minus y is cosine of y, sine is odd, so cosine of minus y is minus sine of y. So that's why we're getting this expression over here, and that's just the conjugate of e to the z, right? So e to the z conjugate is conjugate of e to the z. Another another thing that we can immediately get from this definition is, well, we can compute the modulus, right? Because we have the real part and we have the imaginary part of this. So just take, this guy's squared plus this guy's squared, square root, and you find out that, well, cosine squared plus sine squared is 1, and you just get e to the x, right? So what you get is e to the real part, is the modulus, right? Okay, so let's look at the graphs, right? So this is the, this guy is the real part, and this guy is the imaginary part. Now, over here, what I did was, I marked, when I look at z on the real axis, right, on the z-axis over here, on the real axis, z on the real axis. So basically when y is 0, right? So I've marked in bold the graph over that, right? So you can see over here, we're just getting this nice, if I look at the real part, right, I see this nice shape, the sort of the classical shape of the exponential, right? And over here, I see just 0, right? Well, that's immediate from from these formulas. When y is 0, it's just e to the x, and there's no imaginary part, right? It is real, just what I would want to happen, right? Because if I'm trying to write this and z is real, I really want to get the same thing as I'm getting for for the real exponential, right? So okay, so we're getting this nice exponential shape over here, but notice that so that's what's happening in the real direction, but in the imaginary direction we're getting this sort of sine wave behavior. So you're getting kind of exponential in the real direction, sine wave in the imaginary direction, right? And the sine wave is here as well. It's just for small x's as well. It's just harder to see over there because it's so big over here, right? The magnitude of these waves, right? The size of these waves, the amplitude is bigger for bigger x. All right. So one of the basic properties of complex numbers, of complex exponential, well, of exponential is the laws of exponents. E to the z plus w is e to the z times e to w, right? And this just follows from some trig identities. Now, actually what happens is that if you take just, the actual proper definition, and we'll do a proper definition of the exponential, not this quick one, where we not gonna need the real exponential, and sine and cosine. What you could use is then, you could prove this formula, and from that you would prove those trig identities, right? So it depends on where you define and what you prove, right? But here, at this point, it would require those trig identities. Now, I said a little bit more about this e to the I theta, right? So this is called Euler's formula, right? So again, it could be something that you prove, or something that's, well, at this point, it's, we defined it, right? So it's not something that you prove. All right. So now, if we have this formula, what we can do is we can solve for cosine and sine. I mean, after all, cosine is the real part, sine is the imaginary part, right? So I can write down cosine theta in terms of the exponential, the complex exponential, right? Using this guy over here. But notice this e to the minus I theta. This is just the conjugate, as we saw before, right? So this is e to the I theta plus the conjugate of e to the I theta divided by 2. That's the real part, right? So we have a nice formula for cosine of theta, right? And the same thing for sine, right? And once we have these formulas, well, we could just use them to define complex sine and cosine, right? Just stick in complex numbers instead of the thetas, right? And so that's what we're getting over here, right? We're getting cosine of z is e to the iz plus e to the minus iz divided by 2, right? So once you know the complex exponential, you know cosine and sine, and on real numbers, all these things agree. All right. So technically, we want to look at, in terms of the exponential as well, is polar coordinates for the complex plane. If you remember from calculus, polar coordinates are where if you have Cartesian coordinates x and y, you set x to be r cosine theta and y r sine theta, right? And the way that worked was that if you had the x-axis, the positive real axis over here, then theta is the angle that a line from the origin to your point makes, right? So that's theta, that's the angle, right? And r is the distance from the origin to your point, right? So that's r and theta. That's what these formulas are. But in this case, we have sort of a nice way of writing it using the complex exponential. If you write it, if you just write down the Cartesian form using these calculus versions, right, sine and cosine versions of this, and then you use Euler's formula, you get r e to the I theta, right? So it's a much simpler formula to use for this complex number, right? So that's the polar form of the complex number z, right? R e to the I theta. Now know that r is the modulus, right? I mean, that was the distance to the origin, right? So that's what r is, right? That's the easy one. Theta is called the argument, this angle theta, and so you probably remember, it's not single valued, right? So it has some issues around the origin, for example, but it's even elsewhere. There's many different arguments, right, for the same complex number. So we'll look more at that next time, actually. All right, now polar form is good for multiplication and for powers. Why? Well, suppose that we have two complex numbers, z and w, where z is r e to the I theta and w is s e to the I c, right? And let's multiply them together and use laws of exponents. And you find that z times w is just, well, I just multiply these guys, and use the laws of exponents. And we notice that the modulus is r times s, and the arguments add, right? Now, similarly for, if I divide, right? And again, using laws of exponents, we notice that, well, the modulus behaves like, so if it's r, so 1 over z, the modulus is 1 over r, so that's easy. And the, well, if multiplication is supposed to add, well, division subtracts, right? So 1 over z, the argument is minus the argument of z. Right. Now, similarly for powers, right? Well, it's just multiplying, many different times. So you take a power of the modulus and you multiply the argument by n, right? So it's easy to take powers, easy to multiply, right? So multiplication, what it does is it rotates by the argument, right? Because it adds the arguments together. So if you have one number, what multiplication by the other number does is it rotates everything. It rotates the entire plane. And then it scales, right? It multiplies the moduli together, right? So if you multiply something by a complex number of modulus 2, it scales, it blows everything up by 2, right? Makes all the distances larger by 2, and then it rotates by the argument, right? So that's what multiplication is. And again, if you look at I and write it in polar form, the modulus is 1, so it doesn't scale at all. It just rotates, right? And I is e to the I pi over 2. So pi over 2 is the argument. And so pi over 2 is a quarter circle. It's 90 degrees, right? So what it does, multiplying by I rotates everything by 90 degrees, right? We saw that before with the, was the matrix representation. All right. Now, the downside of the polar form is that it's quite terrible for addition. Oh well, you can't win them all, right? It makes multiplication really nice. It makes taking powers really nice, but addition, yeah, that's ugly in terms of polar form. Yeah, oh well, it goes the other way as well, right? I mean, Cartesian form is really easy for addition, right? It's really nice for addition, and it kind of sucks for multiplication. Maybe it's too bad, but it's, like multiply a whole bunch of numbers together in Cartesian form, and you get sort of these longer and longer expressions, right? And take the write down what the nth power, right? And it's an ugly expression where it's really easy in polar form, right? So if you have to multiply a lot, use polar form. You have to add a lot, use Cartesian form. Maybe one moral of this story. All right. So next time, what we're going to look at is look more at the argument, what the argument does, and all the bad things about the argument, and well, maybe not all of them, but at least some of the bad things about the argument, and we're gonna look at mapping properties of the exponential. All right, so see you next time.